Our architecture analysis consists of Crystal, Changshen, Vivian, and Nicholas. Our team chooses the data analysis topic, in-depth text mining. Text mining is the process of deriving high-quality information from text. Typical text mining tasks include text clustering, entity extraction, sentiment analysis, and document summarization. High-quality information is derived through statistical pattern learning. In this case, we'll be using TF-IDF, which is a way to transform text to numerical features vectors that can be used as inputs to machine learning or deep learning.
TF-IDF, in short for Term Frequency Inverse Document Frequency, it is a numerical statistic that is intended to reflect how important a word is to a document in a collection. It is used as a rank factor in searches of information retrieval, text mining, user modeling, and supervised learning such as text classification. The TF-IDF value increases proportionately to the number of times a word appears in a document, but is often offset by the frequency of the word in the corpus, which helps to adjust for the fact that some words appear more frequently in general. At the bottom of the slides, you can see a short expansion of the formula for TF-IDF. So moving on, the problem that we face is to convert large bodies of text to TF-IDF vectors, which can be time-consuming due to the high dimensionality of the data. So the solution is to work on the efficiency of TF-IDF Vectorisation using MapReduce. Our objective is to input the data, and we run the data through normal TF-IDF algorithm, and we also implement TF-IDF with MapReduce and run data through it. Ultimately, we would want to compare the time taken to run the dataset through both algorithms.
The diagram here shows our implementation of the TF-IDF process. As shown in the diagram, we had to calculate the following variables: the term frequency and the document frequency. We read the raw data, which was in an XML-like format, and processed it to retrieve the list of unique words. We used MapReduce to calculate the document frequency, which is the number of occurrences which the record appears in the entire document. We then retrieved the map of term frequency using multithreading and callables, and the vectorizer then joins both frequencies together to calculate the final TF-IDF weight vector. The first dataset we used was the multi-domain sentiment dataset, which contains reviews taken from Amazon for various product types. For this project, we used a subset of data taken from 3 categories: electronics, kitchen, and books. The snippet below shows the format of the dataset we used, which uses a markup language similar to XML, containing text such as unique ID, the product type and name, and the rating and the date which the review was written. However, we realized that the previous dataset was not enough to show the difference between the serial and the MapReduce functions. Thus, we tried out the food data from the AA practice problem for week 6, which contained over 500,000 rows of data. Similarly, the data consisted of fields such as product ID, review scores, summary, and text.
So it all begins with transforming the data and cleaning the data to a format where it's suitable for data analysis and extraction of information. So in processdata.java, we do this. We first start with load stop words. Load stop words basically is loading a list of predefined words that are not useful in helping to extract information from the data. These words are usually words like the, she, he, is, and etc. So we load this data into a list of string. Next, we call process data 1. So process data 1 and 2 are actually methods that are used to transform our different data sources into to extract the review text, which is what we are interested in, and clean this data up. So the after effects of this is shown here. So this is the data from the Amazon product review. It was in an XML-like format, and it's being transformed into rows where each row represents a review text, and it begins with the ID. followed by the review text. And for foods.txt, the review text is extracted, so where each row represents a review text. The data is being transformed to the correct format, we can begin our TF-IDF vectorization process. So it begins with create vocab and create a word to integer ID. Why we transform the words from string to be represented by integer is because processing or integer operations consume less memory than string operations, and this is especially important in the later steps where we feed the data into machine learning models. So after creating the hash of word to numbers, where you run through the entire document and transform each word into its unique number. So this is called reverse indexing, where we iterate through every word and using the hash map, replace the word with its unique identifying numerical ID. After transforming the entire dataset into a numerical format, we need to get the document frequency for each word. So document frequency is basically the number of documents each word appear in. So for example, I may have 500,000 documents and the word apple may appear in 20,000 of it. So the document frequency is actually a hash map of integer and integers, where the key is an integer representing the word and the value is the integer representing the number of times this word has appeared in for the entire document. It is finally time to get the TF-IDF weightage for each of our words. So get TF-IDF vector actually transforms the entire document into a list of double arrays, where the first value is the numerical ID of the word and the second value is the TF-IDF weighting. When we run this code, we will transform the entire document into a list of double arrays as seen in the output. The explanation for the serial or the sequential way of doing TF-IDF vectorization, where we only use a single thread and everything is done sequentially. So next I'll be going through the MapReduce and callables way of doing TF-IDF vectorization. So the first part is the same as previously, where we transform the entire document into a numerical format. The parallelism begins in the document frequency and getting of the TF-IDF vector. So get document frequency is actually the MapReduce way of getting the document frequency for each unique word. The input would be a list of integer representing the entire document, and in the mapper, the key would be an integer representing a unique word, and the value would be number of occurrence of the word. In the reducer, the key would be the unique word, and the value would be the sum of all the number of occurrences in each of the previous shards. Get TF-IDF vector. It actually makes use of callables to parallelize the process of transforming our data into a TF-IDF vector. Divide the dataset into the desired number of threads and create a list of TF-IDF callables with each subset. And we use fork join pools invoke all method to start the process for all the threads. TF callable, we run through each item in the list of integers and obtains the term frequency for each word in each row of data. And the second part would be obtaining the inverse document frequency and creating the double array pair, where the first index is the word ID and the second index is the TF-IDF weightage. When we run our MapReduce TF-IDF vectorizer, we will get the same output as the serial TF-IDF vectorizer, where we obtain a list of double arrays, as shown in the output below. In summary, we have used streams for data transformation and text preprocessing, and we use MapReduce and callables for feature extraction and vectorization. Ultimately, we'll have an output of TF-IDF with vectors for each document. Let us compare the performance difference of the MapReduce method versus the sequential method, and we have plotted a scatter plot for each of the methods. And as we can see, both follow a somewhat linear growth rate, where as the number of documents increase, the time increases at a linear rate. However, the growth rate for MapReduce method is slower than the sequential growth rate. This means that as the number of documents increase in the long run, the time taken for the MapReduce method will be smaller than the time taken for the sequential method. And for the sequential method, for the dataset with 450,000 documents and 500,000 documents, we were unable to execute the program as encountered an out-of-memory exception. In summary, the sequential method actually performs better when there are lesser number of documents, such as below 250,000 documents. However, from 300,000 documents onwards, MapReduce consistently performs better in the long run. We have come to the end of our presentation. Thank you for your attention, and we hope that just like us, you have learned something new today.